did her master's at the University of Oxford, then went to Switzerland for the PhD studies to the Paul Scherrer Institute, to ETH Zurich, got her PhD in 2017, which means she's now approximately 5 postdoc years old, right? And I'm putting it that way because today is her birthday. I'm not asking you everybody to unmute and sing, but if you go there on Zoom on the bottom bar and click reactions, then you can choose the tada function, the confetti. So, okay, there we have it. 15, 14 tadas. Okay, happy birthday. And still she agreed to present her work here on our online conference instead of enjoying cake with the family. And well, she's very well known for her work on 3D systems, and also her PhD thesis got a lot of prizes for the Richard Green Dissertation Award, Werner Meyer-Ilse Memorial Award, ETH Medal, SPS Award for Computational Physics. And then after a postdoc at Zurich, she moved on to Cambridge and is now, after a lot more awards, a Lise Meyer group leader at, or Spin 3D is your group called, right? At the Max Planck Institute for Chemical Physics of Solids in Dresden, Germany. Everybody welcome Claire Donnelly.
Thank you very much, Jan, for the introduction, and also for the, let me just try to share my slide. I hope you can all see this. So thank you for the introduction, and thank you also for the invitation to speak to you all today. I'm really happy to be here and to see a few of the talks and everything. It's really a really nice meeting. Okay, so I would like to let's see, start. As Jan mentioned, I work on 3D magnetic systems, and today I'm going to be speaking to you about our work visualizing 3D magnetic spin textures, and this we do most of the time with X-rays actually. So just a very quick note, as mentioned, I'm now at the Max Planck Institute for Chemical Physics of Solids in Dresden, where I started my group last year. But of course, I'm not going to be showing you all the work from, let's say, the last 9-10 months. I'm going to be showing you some work from my time in Switzerland and in Cambridge, hence the extra affiliations at the top of the slide. So when we think about visualizing 3D spin textures, I guess the question is, why are we interested in 3-dimensional systems at all? And that's where I thought I'd start in terms of trying to a little bit of motivation. And I think when we think about, let's say, nanomagnetism in general, and a lot of the work that's been done over the last few decades and what we're seeing today as well, the vast majority of very interesting work involves 2-dimensional or planar systems where you can get, let's say, 2-dimensional spin textures or devices, and there's a huge amount to be done. However, what we're interested in is taking this up to the next dimension, i.e. to 3 dimensions, where you can see with the schematic that when we do this geometrically, we already get a huge increase in the number of shapes and geometries that become available to us. And what's particularly interesting is that when it comes to the magnetic properties, we actually benefit as well in terms of, let's say, the magnetic behavior in 3 dimensions. For example, if we think about the most, let's say, well-known application of magnetic materials, we obviously think, or one thing that we think about is magnetic hard drive. Now this is, let's say, encodes your data on a 2-dimensional array of magnetic domains, or let's say logical bits, where you can have magnetization pointing in different directions. It encodes your 1s and 0s. However, it is on a 2-dimensional planar array. And in order to, let's say, to go to higher densities, what people have been working on over the years is really shrinking this down. However, there's of course a fundamental limit. You can only go so small. And that's where, let's say, a proposal from Stuart Parkin comes in, who proposed back in 2008 the idea of going to 3 dimensions to gain this increase in the density of data storage. Now this is known as the racetrack memory. It essentially involves like a 3D architecture of magnetic nanowires, and you would encode your domain walls in the nanowires and move them through, let's say, through this 3-dimensional system. Now, as well as, let's say, getting an increase in the density of devices, going to 3D also impacts the behavior, as I mentioned, of these magnetic materials. For example, there's promising let's say, predictions for domain wall dynamics, so ultra-fast domain wall velocities, magnetochirality effects, etc. And indeed, first experiments, mainly done by the group of Olivier Fouchard, have shown that indeed quite high domain wall mobilities can be observed in these cylindrical nanowires, so higher than you would expect for an equivalent planar system. Essentially, we have a suppression of the Walker breakdown. As well, beyond, let's say, nanowire systems, we also have, let's say, advances when we come to 3D spin textures. And when we think about topological textures, I think all of you will be familiar with this image. This is the magnetic skyrmion. It's shown here distributed on a planar in the plane. However, when we think about how skyrmions, let's say, manifest themselves in reality, they often within, let's say, films that have a real thickness or have or are indeed in thicker crystals. And in those thicker systems, we have the possibility for skyrmion tubes to occur. So these skyrmions form tubes within the thickness of the material, but then also there's the possibility of transformations of the topology within the thickness that can involve the presence of singularities of the magnetization. And one last point to mention is that we're also particularly interested in is going even up to the next dimension with topological textures, that is to magnetic ophions. So these are really the three-dimensional equivalent of a magnetic skyrmion. And so far, let's say they've been observed, so ophions have been observed in different material systems. So for example, in liquid crystals, they've been found. And there have been recent predictions for them to also occur in ferromagnetic systems. And there's been a first experimental work done by the group of Peter Fisher, where they think that they might have, let's say, seen a texture that could potentially be a magnetic ophion. So this is a really interesting direction, and there's, as you can see already from this slide, when we think about going to 3D, there's many different aspects that are particularly motivating. So this is generally, hopefully with this slide, I've been able to motivate you a bit for going to the third dimension. And now on to what I'm going to be speaking to you about in the rest of the talk. And that is, as I mentioned to you, we're going to be talking about imaging these systems with X-rays, so three-dimensional spin systems. Now for that, what we first of all want to do is we want to image 3D magnetic textures. We already said that their behavior is particularly motivating, so we want to look at their behavior, ideally by, let's say, doing time-resolved 3D imaging. And lastly, I want to introduce a bit of more recent work that we've been doing on three-dimensional magnetic nanostructures, where we can really pattern magnetic materials in 3D geometries and control their behavior that way. So key to all of these, let's see, points or sections is the ability to visualize spins in 3D. And that's what I just want to introduce very quickly. First of all, the idea of magnetic tomography. So if we think of tomography, this is the same technique as you would have in the CT scan in the hospital. What essentially you have is you have a 3D sample in the hospital, it's your body or your arm, and you take transmission images from many different orientations of your structure. And essentially what you then have is that you have a collection of two-dimensional images taken from many different orientations. You can use a reconstruction algorithm to reconstruct back to the internal configuration. And it's this idea that we apply to magnetic systems in order to implement magnetic vector tomography. So the three basic ingredients are being able to image 2D projections of the magnetization. For this, we probe the X-ray magnetic circular dichroism, which is a resonant effect, and we use synchrotron X-rays in order to do this. We can, in this way, collect images with nanoscale spatial resolution of the magnetization component parallel to our X-ray beam. Now we have then our 2D ingredient, or our 2D images, which are a basic ingredient of the technique. We next need to be able to measure from many different orientations, and the question is, how much data do we need? And it soon became clear when we were thinking about this that actually a single rotation axis is not enough. So actually, in order to probe all three components of your vector field, you need to measure more than one tomographic rotation axis, or many different orientations of your sample. And lastly, we have our 2D projections measured around many different orientations. We need a reconstruction algorithm, and this is something we've developed in-house. We've developed our own algorithm, but there have been other groups that have also developed algorithms. For example, the group of Aurelio Hierro Rodriguez, who's worked with his colleagues in Alba in Spain. And essentially what we are able to do now is to be able to really recover our 3D vector field from our experimental data. So we can have a first look at what kind of textures we can see when we look in 3D at a sample. And specifically, the first sample that we looked at was this gadolinium cobalt pillar. Here, this is a micropillar, so it's 5 micrometers in diameter. We therefore use hard X-rays in order to be able to, let's say, transmit the X-rays through such a large piece of material. And the key thing is that before we, let's say, did this measurement, it was not known what was going on inside this sample. So it's too thick to measure in any other way internally. And actually computationally, it's also very difficult to simulate such a large system. So we perform magnetic tomography, and with this technique, just to give you a bit of an idea of what the kind of data that we get, we are able to map out the vector field with this nanoscale spatial resolution, in this case 100 nanometer spatial resolution, throughout the thickness of the sample. So for each point within the sample, we get in a direction of our magnetization vector. And you can see that within the sample, there's a number of different features, let's say, and the magnetization is mainly smoothly varying, but there's a number of different kind of twists and turns that are occurring. And indeed, when we take a little bit of a closer look at what's going on, we were able to observe a number of different structures. So we can see, when we take the cross-section, we can see vortices, and we can see anti-vortices, which are more like saddle-like structure. We can also see, when we look in 3D at the crossover of, for example, vortices and domain walls, we can see the presence, or we can, let's say, determine the presence of singularities of the magnetization. Now, these are particularly interesting because, well, first of all, they're also known as block points. They were first predicted back in the 1960s by Feldkircher. What's particularly interesting is that they essentially represent a topological defect. So if you imagine you have your topological system and you want to change the topology of the system, this will be associated with the presence of a block point within the volume of your structure. Now, we were able to find a number of these within our system and map out the surroundings of these singularities. And you can see that we were able to observe circulating block points, and then also a more twisted anti-block point state. So there's this kind of, like you would have a vortex and an anti-vortex, we have a block point and an anti-block point that have opposite topological indices. So with this, we have a first kind of idea of the type of structures that we can see within such a three-dimensional magnetic system. But as you can imagine, such data sets come with a main challenge. That is, how do we actually, so within these large data sets, which have millions of pixels, each with 3 components of the magnetization, how do we identify the relevant objects? So how do we work out what is interesting, what we want to find within our system? And for this, we've actually developed a new way of analyzing our data based on the fact that we know that the relevant objects within our data are topological. We're interested in topological magnetic features. So we implement calculations of the magnetic vorticity vector. Essentially what this is, it's the flux of the skyrmion number density. So it kind of encodes the topology of our system as a vector field. And when we plot the magnitude of this vorticity vector within the structure, what we see is we are able to observe or map out a network of structures. Now, these tubes correspond to cores of topological objects, and the majority of these here are vortices and anti-vortices. But in this way, we're able to see exactly how the vortices and anti-vortices form a complex network within the bulk of our system. Now, we can also, let's say, go one step further, and we can think about these block point singularities, right? I said that they are associated with a change in topology. So if we plot changes in the magnetic vorticity vector, i.e. regions of high divergence, we can actually plot out or map out the presence of block point singularities within our structure. You see here, this is a very nice way to immediately get the presence and location of, I think, more than 50 block points in a single calculation. And it's, I think, pretty powerful method because it shows that we're able to really now look at the distribution and potentially interaction of these structures in 3 dimensions. And just to mention, for those who are interested in this kind of techniques, a similar analysis was done by, again, Aurelio Hierro Rodriguez and his colleagues in Alba. And so I would really recommend checking out this publication if you're interested. Okay, so far with our magnetic vorticity vector, we've been able to map out and locate relevant structures. But we can actually use it for more than this. We can use it to understand certain features that we have observed within our magnetic configuration. So specifically, one of the structures I want to speak about to you today are these loops that we observed within the magnetization. So now these are loops where the loop consists of the core of a vortex you see on the left-hand side and an anti-vortex on the right-hand side. And the core forms this loop, which is about 300 to 400 nanometers in diameter. Now the question was, why are these vortex-anti-vortex pairs occurring in such a kind of confined structure? And it wasn't until we mapped out the magnetic vorticity that we realized that the vorticity vector is circulating. What this means is we have magnetic vortex rings. Now, interestingly enough, these were predicted back in the 1990s by Nigel Cooper, who was a co-author on this work. He was in Cambridge when I was there as well. And what was very interesting was, speaking to him and reading his old paper, was that these magnetic vortex rings, they're really the analogy of their hydrodynamic equivalents, right? So they're directly analogous to these bubble rings or smoke rings that we see in fluids. Also in the sense that, let's say, as you would have a smoke ring that is stable as it propagates, magnetic vortices or magnetic vortex rings are also predicted to be stable as propagating structures, but they're not supposed to be stable statically. So this was one question that we had. So why do we see these statically? I mean, our measurements take about 50 hours. They're definitely static and stable objects. And this led us to go on to consider what could possibly be causing this stability. Now, the first thing that we, of course, thought of was the topology of the vortex ring. Could it be that we have a topologically non-trivial structure? And in order to plot this out or to determine the topology of our structure, we could take inspiration from our colleagues working in magnetic Hopfions and plot so-called pre-images. So these are isosurfaces where the blue and the red correspond to different directions of the magnetization. The fact that they link means that it's topologically non-trivial, it has a Hopf index. Now, when we plot this for our data, unfortunately, or let's say, first of all, we were a bit disappointed because the loops do not link, meaning that we do not have a Hopfion. This is a topologically trivial structure. But in a sense, this was even more intriguing because topology is not causing the stability. So then what is? So we went on to, I don't have a, let's see, extra slides on this at the moment, but we went on to have a look at different types of, whether we could see more of these. We saw a number of these within our configuration. And by working together with our colleague, Konstantin Metlov, he performed analytical modeling. We were able to determine it's actually the magnetostatics that are stabilizing these structures, showing that magnetostatics are important for 3D configurations. Okay, so that was just a quick insight into the types of structures that we can see statically in our magnetic, with this 3D magnetic vector imaging technique. Now the next point on our list, the next point on our to-do list was to work out whether we can look at their dynamics. So to be able to image the behavior of 3D magnetic configurations, again in 3D. So the question, first of all, is more a methodology question. Can we simply apply our tomography technique to dynamic imaging? And there is a challenge here. The challenge is that let's say, if we think about a typical dynamic sample, we want to put contacts on, right? And for that, we use a flat sample, typically a silicon nitride membrane. When we rotate our silicon nitride membrane, at some point we block the beam, meaning that we lose information. Now, this is a problem because it can create artifacts in your reconstruction. So now, in order to get around this problem, we go to an alternative geometry, where rather than rotating our sample around the north, let's say an axis perpendicular to our X-rays, we actually tilt the rotation axis towards the X-rays, and in this way we never actually block the beam. And this is known as laminography geometry. So this is compatible with the patterning of strip lines on our sample with which we can excite the sample. And specifically in this case, our sample is a gadolinium cobalt disk, about 1.2 micrometers in thickness, 5 micrometers in diameter. We're exciting it with the Ørsted field of our strip line. We're passing an AC field, an AC current through the strip line in order to get an AC Ørsted field. Now, what we do essentially in order to get our time resolved data is we take advantage of the time structure of the synchrotron, where we have pulsed X-rays coming at 500 megahertz. So we can excite our sample with a 500 megahertz excitation and essentially perform pump probe measurement. So we measure for different time delays with respect to, between our excitation and our X-rays, and therefore essentially acquire time resolved 3D data sets. So we have our data, and first of all, let's have a look at what the static configuration is before we go into the dynamics. So the static configuration of our disk is as you see here. So one thing to note is that we have a change in anisotropy of our disk and the magnetization of our disk through the thickness, meaning that in the lower half of the structure, we have this double vortex state, and in the upper half, we have a single domain because we have higher anisotropy, essentially creating a kind of exchange spring-like system. So we have quite an inhomogeneous magnetic configuration. Now we can go on to look at what the dynamics of the different, let's say, regions of this sample are in 3D. So let's start first of all with the magnetic vortices that we observe in the lower half of the sample. When we look at our data, what I'm showing you here is a slice near the lower half of our sample, which is a time resolved difference slice. So it's basically taking the difference between each time and a certain reference time. Now the reference time is shown by this white line that you can see here. And what you see is that the vortex domain wall is this dark purple line. It's oscillating from side to side of this reference point, meaning that we can really observe the gyration of our vortex domain wall, let's say about this reference point. Now this makes sense magnetically. People have seen such behavior in 2 dimensions, but it's never been done really looking within the bulk of a system. We're able to, because we have access to the 3D data, we're able to really track the location of our vortex core across, say, the period of the excitation, determine its velocity, and essentially, let's say, map this out through the thickness of our system, demonstrating first of all that it is possible to track topological objects and their motion in a 3-dimensional system. But we can go one step further than that, and we can actually perform Fourier analysis on our 3D data in order to map out coherent rotation modes of the sample. So essentially what we're showing here, the red regions are regions where we have the magnetization oscillating at 500 megahertz. And we see then throughout the thickness of the sample that we have a quite large change in dynamics through the thickness. In the top half, where we have this single domain state, we have more edge modes occurring, and in the lower half, these edge modes sort of circulate around the edge of the system, and in the lower half connect to the vortex domain walls, showing that we have a strong, let's say, link between our magnetization dynamics and the 3D sort of magnetic structure that we saw statically as well. Okay, so so far I've been speaking about, let's say, larger scale systems, and in the last 5 minutes or so of my talk, I want to zoom down to smaller length scales and specifically go on to talk about 3D magnetic nanostructures that we pattern really on the nanometer length scale. So when we think about going to smaller length scales, we need to go to soft X-rays, and essentially why this is because we have, let's say, smaller, we have more absorption, we get more contrast, and we get higher signals with the XMCD in the soft X-ray regime. So we've recently implemented soft X-ray laminography with STXM at the Pollux beamline at the Swiss light source, where now that everything is in soft X-rays, everything has to be in vacuum, it's all quite tight. You can see here from the design that Katerina Witte, who was a postdoc at PSI, implemented this really nicely. So this is really a photo of the actual structure with the rotation stage here and the optics and the beam coming out here. And this allowed us to do a first sort of proof of principle demonstration of soft X-ray laminography, where we were able to map out the structure of a magnetic skyrmion, or magnetic target skyrmion state. So this was done, a sample fabricated by Simone Finizio. So what this showed us, that this is, let's say, a 200 nanometer thick permalloy disc. It showed us that we can really go to the small length scales, meaning that it now makes it possible to probe 3D magnetic nanostructures. Now, there is an added advantage of going to STXM, and that is because scanning transmission X-ray microscopy is ideal for time-resolved imaging. This is because we have a point detector, and it is fast enough that we are not only limited to the frequency of our synchrotron, but we can actually excite our system at different frequencies and therefore probe resonant dynamics. So Simone also earlier this year had a nice paper published where we demonstrated this on an anisotropic vortex state, so basically a Landau pattern that has some magnetic anisotropy, and whereby using this time-resolved STXM as the 2D imaging technique, we were able to probe both the vortex core gyration, but also the excitation of the domain walls at a higher frequency. So this kind of shows, I just want to mention for everybody out there that if you're interested in imaging 3D systems with time resolution, then this is a technique that is currently available at the Swiss Light Source. Okay, but just in the last few minutes, what can we do with this? And I mentioned we wanted to look at three-dimensional magnetic nanostructures. Specifically, if you think back to the start of the talk, we're interested in going to 3D because of the prospects for higher density, but also new types of dynamics, let's say, and different magnetic states when we go to 3D pattern systems. Now, when we think about such a device, not only do we need to pattern it in 3D, but we need to understand what the influence of introducing these regions of curvature are, and potentially highly packed systems. So we have a model system, which is a double helix nanostructure, which combines curvature and dipolar coupling. And essentially we can pattern this with a technique known as focused electron beam induced deposition, where we can really realize magnetic nanostructures with 3D arbitrary geometries. And when we go to soft X-rays, we can probe their state magnetically. So here you see that we have one helix is black and one helix is white. This means we have them pointing in the opposite directions. But when we apply a magnetic field, we're able to trap domain walls in a regular array along the helix axis. Now the question is, what effect does the 3D geometry have on these domain walls? Well, for this, we apply our 3D imaging technique. And we're able to actually, so this data looks a lot noisier because we're really at the limit of our resolution. But what's very interesting is that we're able to see that actually, if we think about the domain wall, or how the magnetic domain walls were initialized with the magnetic field, our domain walls are pointing the opposite direction. So we can apply micromagnetic simulations, and we're able to realize this, so we can reproduce this reversal of the domain wall orientation, which is essentially due to the interhelix coupling. So if we had only had one helix, our curvature would prefer to point, let's say we have curvature induced effective anisotropy. Our domain walls should point in the direction of the magnetic field, but because of the coupling in between the domain walls, we have this reversal which closes the flux. Now, what is even kind of more interesting is if when we think about what's actually happening to the induction in between these domain walls, we can see that when we consider the highest strengths of the magnetic stray fields, it's almost horizontal. But as we look at, let's say, weaker and weaker fields, we see a tilting of our magnetic stray field, meaning that we have basically channeling of the flux between like domains. Now, this is only possible due to the twisting of the helix, due to the chirality and curvature of the helix. What's particularly interesting is this twisting and curvature leads to an interesting feature in the magnetic induction. So if we plot our magnetic stray field in this plane, we see that, of course, we have our magnetic domains in our helix that are kind of creating almost like vortex-like structures. But around the domain walls, we get effectively anti-vortices in our magnetic induction. And this is analogous to kind of our, let's say, in two-dimensional systems where you would have a cross-tie wall, which is formed of vortices and anti-vortices. Here we have an effective cross-tie wall, which is formed of the chirality of our double helix and then anti-vortices occurring around our domain wall structures. Okay, so I think this is me out of time. So just want to say quickly a big thank you to everyone who's been involved in this work. There've been a lot of people in Switzerland, in Spain. I'd like to particularly thank Laura Heidemann and my colleagues at the Swiss Light Source. And to conclude, I've spoken to you about statics and dynamics of 3D magnetic systems, also in magnetic nanostructures. And there's a lot to look forward to in the next few years, hopefully. So more than happy to answer any questions. Thanks again.
Thank you, Claire, for the wonderful talk. We have questions. We have a lot of questions, I think. And the first one actually came on the chat, and that was by Alberto. Alberto, do you want to unmute yourself and ask the question? No? Well, the question is, can you do the time-resolved STXM in single-shot mode, or do you integrate over a few X-ray pulses per image? What is your time resolution?
So that's a very good point. It's not single-shot mode. We have to integrate. Part of the problem with tomography is that we need to measure many orientations, right? So it's going to be intrinsically an integration method. But what we essentially do is we need a reproducible motion, so it has to be reproducible, and we measure it. In the end, we're averaging billions of times. But in principle, let's say single shot mode would be limited to two-dimensional imaging. 3D imaging is sort of intrinsically or fundamentally incompatible with that. And time resolution, the time resolution of the synchrotron is about 70 picoseconds, but Simone and his colleagues at the Pollux beamline at the Swiss Light Source have been able to, let's say, bring the spatial resolution of the technique slightly down to slightly below 70 picoseconds.
Okay, the next question is by Jack. Who can also unmute himself. Okay.
Thank you for the lovely talk, Claire. I was wondering, with the magnetic vortex rings, you said they were stabilized magnetostatically. I was wondering if you just comment on which energy terms in the magnetic interaction are responsible for this stabilization.
Okay, so this was something that we I can explain to you how we came to that conclusion, essentially, if you want. So what we did, I mean, typically in the work of Nigel Cooper, he only had exchange in his system. So what he concluded is that you need some nonlinear interaction in order to stabilize such so these kind of higher order features, and they need to be stable dynamically. Essentially what we did, or I say what we did, what Konstantin did, was he developed a model for these vortex anti-vortex pairs that was based on the model of a cross-tie wall, but in a very, very thick system. So he extended this to almost an infinitely thick system. And what he found is that there was an associated typical length scale when it was just balancing purely exchange and magnetostatics. A typical length scale associated with the distance between the vortex and then the anti-vortex in this cross-tie wall. And this matched, so first of all, magnetostatics meant that it was possible for this to be a stable state. Secondly, this length scale matched pretty well to the length scale that we observed in our system. So maybe something I forgot to mention was that we saw a number of these vortex rings. What was really interesting was that they were they were always the same size. So they always had a diameter, I think, of about between 300 and 400 nanometers. We saw, I think, 7 or 8 of them, all with this size. And this matched pretty well to Konstantin's model. And this was how we concluded that it's probably the magnetostatics that is helping to stabilize the structure.
Okay, thank you.
Thank you.
And then there is a last question by Viviane.
Thank you for impressive work, Claire. I was just wondering, in your last example, since the structures are turned, if there is during the pin of the magnetic moment, if there is a problem with local Joule heating during the application of the magnetic field.
Okay, so that's a really good question. Thanks, Vivian. So in this current measurements that I mentioned here, geoheating is not a problem because we don't apply any current. We apply global magnetic field simply with a permanent magnet, actually. So this is how we initialize our domain walls. But I think in this, geoheating is going to be definitely an issue when we come to actually applying current and trying to excite these domain walls. If we, you know, for example, if we can apply a current through the system, and I know the group of Olivier Fouchard have seen this, that the heating effects in cylindrical nanowires are incredibly important and seem to be dominating them. We are not yet at the stage where we're applying current through these systems, but it's something that we're planning in the next, let's say, hopefully 6 months or so. So but I'm sure this is going to be a problem that we'll come across.
Yeah, thank you. Thank you.
Okay, so Claire, thank you once again for the nice talk, for answering all those questions. And let me first hit the